Okay, let's get started with the third session, paper session of IWOMP. Welcome, everyone. This session is about new performance and correctness tooling. Our first author is Ethan, and he's going to talk about profile generation for GPU targets.
All right, thank you. So, as she said, my name is Ethan. I'm going to be talking about profile generation for GPU targets. I worked on this project as an intern at the Lawrence Livermore National Laboratory, and I worked on it with Joel E. Denny from the Oak Ridge National Laboratory, as well as my mentor, Johannes Dörfer, at the Lawrence Livermore National Laboratory. So as that introduction would suggest, this project was funded under the auspices of the DOE, LNL, UT Battelle. And now that we got that out of the way, let's talk about some background. So what is PGO? PGO stands for Profile Guided Optimization, and it's a process that involves the compiler optimizing a program based on how it's used. We can break this process down into 3 separate steps. So the first step is instrumentation. This is the part where we create counters associated, and in those regions, we insert counters to the respective globals. This way, we can tell exactly how many times each region of code executed. And instrumentation can occur on either the front end or the LVMIR level. The front end does instrumentation on the Clang AST, whereas the IR level happens later on the generated LVMIR. The next step is profile generation. This is the part where we run the program and collect the data related to the counters we created. So this step is performed by the compiler-RT profiling library, which is responsible for gathering the data from the counters and writing them to a profile file. We can then use this profile file with LVM prof data to create a prof data file, which then leads into our next step, optimization. This is the part where the compiler actually uses the data to make informed decisions about how to optimize the code. So PGO data can impact things like block placement, inlining, indirect call promotion, things of that nature. This is where we're supplying the data via fprofile use, and the optimizer is doing its optimization sensitive passes are doing their thing. So a little bit of background on kernel info, because this is going to become relevant later. So kernel info is an LVM analysis pass, and it runs later in the pipeline after all the LTO passes are done running. This pass analyzes static GPU code. So it'll do analysis on, it gathers insights based on kind of the final LVMIR before we lower it to the GPU device code. Things like stack allocations, launch bounds, direct and indirect calls, and So it uses the LVM remark system to emit diagnostics in the form of compiler remarks and YAML reports. And it's currently a work in progress. We can kind of see its progress here. The faded out portions haven't been implemented or haven't been upstreamed yet, but there has been some work on that this summer, not involved in this project. So why are we doing this? We have this rich PGO ecosystem on the CPU that wasn't designed for the GPU and formerly couldn't run on the GPU. And there have historically been some concerns about extending support to the GPU for profile instrumentation. And one has been that maybe the overhead that these counters create might be just too much for some HPC programs. Because when you're running things in parallel at a massive scale, those little increments really add up to a lot. Another concern was maybe that high performance computing programs would overload the counters and make them overflow. So for this project, our goals were just to implement it, just to make sure we can get it to run. We want to see what works, what doesn't. Another goal that's related to this was just seeing how the PGO optimization passes worked on GPU targets. They were designed for CPUs in mind, and we wanted to see how they would run on this new ecosystem. And we also just wanted to see what tools we can use with these generated GPU profiles. So let's talk about the changes we made to the instrumentation passes. So what we did was we had to make sure, the first step was making sure that it actually ran. And the first step in the largest step, was making sure all the address spaces were correct. Because in a GPU, we have the profiling globals, and those are in address space 0 on a CPU, but they're on address space 1 in a GPU. And the profiling intrinsics, they expect an unqualified pointer of address space 0. So we had to add a bunch of casts just to make this pass work. And another step was making sure that these globals are visible to the host on GPU targets, because as you'll see in the next slide, we need to pull those values out to process them and write them. So we also wanted to make sure that these profiling globals worked on NVIDIA. And the reason they weren't working on NVIDIA in the first place was because the profiling globals are basically these structs that have lots of fields, some of which reference the global they're a part of. And that's not allowed on NVPTX targets. So what we had to do is we needed to delay the initialization of those fields specifically into this function called, a generated function called LVM profile delayed data var in it. Long name, I know. But this function call is inserted at the beginning of the kernel, of the compute kernel, so that we can still have the same functionality we would get, but we're playing by NVPTX's rules. Now, this particular part hasn't been upstreamed yet, but I felt it was worth noting. All right, now let's talk about the modifications made to the runtime. So both the OpenMP and compiler RT profiling library have been modified to sort of do this project. So we added a new entry point for the compiler RT profiling library called LVM write custom profile. Now this is kind of a special function we're going to be using in the OpenMP. We're going to be calling from the OpenMP runtime that takes a target name and custom data. So what it does is it writes a separate profile, separate from the host, that's prefixed by the target name. It's another prop profile that doesn't, important, it doesn't interfere with the host. And that's going to contain our device's profile data. So as far as the OpenMP library goes, we had to modify, the OpenMP runtime goes, we had to modify that as well. In device deinitialization, we iterate through the globals on the device elf file. And we look for things that start like proxy, things that are generated by this instrumentation pass that we want to include in our device profrom. So we look through those and we query the device plugin to get those values from the GPU before it deinitializes. And then we call this aforementioned entry point function with our data and our target, and that writes the separate file. So, and I should note that a weak link to this particular entry point is included, a weak definition for this entry point is included in the OpenMP library, so that it builds well, but we can also detect if it's not there and throw an error and say, you have profiling globals, but you do not have a profiling library. So how do you run your own instrumented GPU programs? So Clang now passes the GPU, the instrumentation flags to GPU targets when you're running an offloaded program. And it'll pass it both to the host and the device. And right now, upstream, this is only AMD, but in the future, it will likely be NVIDIA once we get that upstream. If you only want to profile the device, you need to use xarch device along with your profiling flag. But you'll also need to add fprofile create, just so that the profiling library gets linked in on the host as well. So you'll see an example of an invocation here, the device profile, host profile, which is empty because we didn't instrument it in this run. All right, now let's talk about the proxy apps we evaluated and just the process of evaluating existing profile guided optimization passes on the GPU. So our first test case was XS Bench. It's a lightweight Monte Carlo simulation for neutron transport. And we compiled it on AMD at 03 optimization with all the profiling flags made. We did a different run for IR instrumentation, front-end instrumentation, and we did builds for optimized instrumentation, optimized builds as well, sorry. Those use the instrumentation data, not the instrumentation itself. So you can kind of see the results of this. For each test, we ran it 100 times, and we documented the result of the XS Bench large test. And you'll notice that the IR instrumentation caused about a 54% slowdown, and the front-end instrumentation caused about a 122% slowdown. Now, these are pretty big slowdowns, but we expected this to happen, right? Because these counters, they're not free. Profiles aren't free. We need to add the increments to make this work. And when you run a lot of things in parallel on GPUs, you're going to get that overhead really adds up. What we didn't expect, however, was what we got when we ran the actual optimized, PGO optimized versions, builds. So here you can see the sort of the full report. And you'll notice that the IRPGO optimized build had a 1.39% slowdown when compared to baseline. Similarly, the front end had about a 2% slowdown when compared to baseline. And this isn't really what we wanted to see, right? When we do PGO, we want to see at least a little bit of a speed up if we're going through all that trouble. But instead, we got a little bit of a slowdown. And it's not a large slowdown, but it still kind of defeats the purpose of PGO. So this leads us into our next test case, which is OpenMC. And OpenMC is another large Monte Carlo nuclear simulation. And again, we built it on AMD at O3 optimization, but this time we only did LVM IR level instrumentation because that was the one that worked the best the last time. We also tested hot-cold splitting, and just to see how that would work as well. And for the test benchmark, we ran the large XXL test in John Tram's OpenMC test benchmarks. And you can see the results on this graph. So much like last time, we had a significant impact in the instrumented, slowdown in the instrumented build, and slight impacts in both the optimized builds. Again, this isn't what we want to see, but we're going to kind of discuss this later in the next slide. There was a 2% decrease in the IRPGO, 11% in the hot-cold split. And in this case, more is better. In the last one we were measuring time, this one's particles per second. So what's going on here? Why is the PGO making our program slower? Well, we believe that this is because the PGO passes were designed for and designed on CPUs to make CPU programs run faster, and GPUs are different, right? So when you pass the compiler data, if it can't meaningfully use that data well, it's just as bad data, right? If we're giving it this data and it doesn't know how to use it well, we're not going to see the optimizations we want to see. So that leads to the question, if profile guided optimization isn't ready on GPUs, then what can we use our GPU profiles for? So we're still generating these files. What can we use them for? And that leads us to our first use case, which is coverage mapping. So coverage mapping does work on GPU targets, and you'll see an example of this in the next slide. Coverage mapping basically allows us to test the coverage for our program. What parts are running, which parts, and how much are they running? So the nice thing about coverage mapping is it lets us see line by line how many times a particular line runs. And for this, you will need front-end instrumentation. That is done with fprofile instr generate and the F coverage mapping flags. And again, these are passed to AMD targets on upstream. Now, for GPU targets specifically, you may have to run the remapping file option because the compute kernels on the device do not always match the names of their host fallbacks. And I've found that generally, if you want to run coverage mapping stuff, you want to have them match. So you're going to want to use that remapping file option. Here's an example of an invocation of that happening. We got process prof data, we run LVM cov, that's the cov utility, the coverage utility. So here are the examples I talked about. The top two examples are examples from a compute kernel in XS bench, and the bottom two are just things that are just like things that run the host for like their validation specifically. And you notice the host has no runs for the GPU kernel, and the device does, right? But the host runs the host code, but not the device code. So we see that reflected in these reports. And I do like the split between just the visualization of the host and device being separate, but the real power this gives you is the ability to sort of monitor your application's performance. Because if we can't rely on PGO just yet to make our programs faster, we can analyze the performance ourselves and tune our programs accordingly. So next use case, kernel info floating point reports. This is the pass I mentioned earlier in the beginning. So we've extended kernel info to report floating point operations, which we'll call flops here, and floating point bytes moved. So we can compute these statistics by combining the static info that kernel info gives us alongside the dynamic counts that we get from the profiling prof rows, or in this case, process prof data. So to get the number of floating point bytes moved, all we need to do for a particular read or write instruction is we need to take the number of bytes that that particular instruction reads or writes, and we need to just multiply that times that instruction's enclosing basic block count, right? That gives us the total number of bytes moved for that particular instruction. Now, computing floating point operations for a particular floating point operation LVMIR instruction is a little more complicated because we need to know specifically how many hardware instructions are executing for this particular LVMIR instruction. And we can call this ratio the flop multiplier because it's how many flops are executing per LVM instruction. So to find this, if we can find this flop multiplier, we can then determine how many hardware instructions this particular LVMIR instruction executes. So how do we find the flop multiplier? Well, our first step was creating a small program for each floating point operation we wanted to test. These are things like fmul, fadd, just simple floating point operations that we put in this target loop on the device. And what we do is we compile this on O1 optimization to avoid optimizing out any critical behavior, and then we run it with rockprop v3. We made sure to only count full warps, and for each hardware instruction we got, we made sure to multiply it by a hardware multiplier we found in the ROCm source. So once we have this total, we divide it by the product of the number of threads in the thread limit, and this gives us our hardware instructions for a single iteration of this loop. Now, we only tested this for 64 bits on AMD, but I'll show you the results. So what did we find? Most multipliers were either 1 or 0. We had a few that were 2, things like FMA, which makes sense since it's multiply and add, and things like float to integer conversions. Those were also 2. There were also more complex operations like fdiv and fsquirt that had larger flop multipliers like 14 and 17. And this is sort of the performance we found for fadd. And you'll note that all the graphs for the other operations look like this. They're just shifted up based on what their flop multiplier is. So let's talk about how we evaluated these new kernel info changes. So we ran 3 proxy apps to test it. We ran XSBench, we ran OpenMC, and we ran RSBench. And we ran them all on AMD at O3 optimization, just like the other tests. For XSBench, we ran the default large test that we ran last time. And for OpenMC, we ran the small test in John Tram's OpenMC benchmarks suite. So each test is plotted on this roof line. The blue ones are the kernel info tests, and the red ones are the rockprop reports. And what you'll notice is that on this roofline graph, the rockprop tests are reported as being much more performant than their corresponding kernel info reports. And this is due to a difference between what the two things measure. So these two tools measure different things. Rockprop measures the number of hardware instructions recorded, whereas kernel info measures the amount of hardware instructions that are relevant to our program specifically. And this is a relevant distinction because hardware counters can mislead developers into believing that their code is more performant than it actually is. Because what happens a lot of the time is, to avoid diverging, the GPU will execute extra operations just to avoid divergence. And this is smart, but it inflates our counts. So take the following work. So we have a bunch of threads, all if statements. Each branch of the if statement has a separate floating point operation, and all these conditions are expected to diverge at some point. So we would expect this count to be the warp size, but instead what we get when we run rockprop is we get the warp size times 2. This is because for each thread, 2 floating point operations are being executed and 1 is being discarded. So this is something called predication, and the GPU does this to make it faster, again, to avoid divergence. It makes it faster, but it does increase the count. Let's talk about another example. So this one's analogous to the XSBench calculate macro XS function. And each thread has a loop iterating over a different range, A, B, C. Now, you might expect the hardware flops to be A plus B plus C, because that's how many flops are running for each run of these loops. But as with last time, rather than diverge the compiler decides to write in extra instructions rather than diverge. So what we get instead is max among A, B, C, and so on, times the work size. Because it's put really well in the paper, even when the application uses all threads in a work, if the work has thread divergence, the count for each thread becomes the maximum count among the threads in the work. So again, the compiler should execute more rather than diverge. And what do we do with this difference? How do we make sense of it? So kernel info's report aren't necessarily more accurate than rock prof and vice versa. They're complementary statistics. They measure different things. And by paying close attention to the gap between these two, we can analyze the gap between what we compute and what we want to compute. And ideally, we want to minimize that as much as possible. So this is the kernel info changes. They haven't been upstreamed yet, but they're in this. You can find the pull request on this particular QR code. You're going to need foffloat LTO, rpass kernel info, and fprofile use to run it. Here's an example invocation. Now let's go to conclusions. So to conclude, we can instrument GPU devices, and this behavior has been upstreamed. So PGO for GPU devices isn't here yet, but we can still glean valuable info from these profiles we generate. We can use coverage mapping and kernel info flop reporting to better analyze our applications and optimize them. And thank you for listening, and thank you to Johannes and Joel for working on this with me. I'll be open for questions now.
Let's time the speaker. Let's do the in-room questions first, and then I'll check online if people have questions. Go ahead.
So I have a question.
Yeah.
In the instrumentation, you said you do kernel instrumentation, like the
GPU code is being instrumented.
So when you're running the LVM pass, then the LVM IR you see, you don't see the kernel code there, right? You see the code if the GPU is not available, which would be deployed, which will be executed on the host itself.
So yeah, in the past we see both. There's a pass that runs on both the GPU code and the host code. They're separate. They run separately. But in the host code gets instrumented as well as GPU unless you specify just the GPU. Does that answer your question, or is there something?
Kind of, yeah. I mean,
but yeah, it's not one whole application. It's two separate things. Any other questions? Yes.
Have you compared the counts between the IR instrumentation and the front-end instrumentation? Do they give you the same?
So the counts between the IR instrumentation and the front end no, they're not going to be the same because they instrument things a little bit differently.
So was that the source of the difference in performance?
Yeah, I found that the front end tends to be less performant than the IR PGO, but you need the front end to source things like coverage mapping. So does that answer your question? Anyone else? Or? Yes.
I missed this, but you were discussing instrumenting the GPU code from within the LVM IR. What method are you using to determine where precisely to place the instrumentation points? Is there a way that you could configure it somehow to place more or fewer of them?
I wouldn't know, but a lot of the instrumentation is reused from what's done on the CPU. So in the instrumentation slide, I kind of outlined the different changes I needed to make it work. But the different points will be inserted into things like if branches, loops, things of that nature where there's conditional execution a lot of the time. And I wouldn't know how to specifically configure it, but I'm pretty sure the IR PGO and front-end PGO insert them differently. Like one uses the playing AST, another uses the final LVMIR. Sort of not final, but later and down the line.
Okay.
Does that answer your question?
Yeah, I was just going to suggest maybe configuring how precisely the instrumentation points are placed might assist with some performance things you would.
Yeah, I mean, some ideas were like, when I was talking about this with some of the people who I worked with, some of the ideas were floated were things like making sort of a new pass to analyze divergence. For example, like in each branch, we have like a different counter and like, it basically involved different types of instrumentation. There is a question to be asked like, okay, how useful are these counts for on GPU? And I do think they're useful as shown here, but there might need to be more instrumentation done on the GPU to gather more data, depending on what we want to do with it. So
Yeah, and if you could, I wanna run some kind of, some kind of analysis to show like, maybe the overhead that you're seeing is induced by a small percentage of the instrumentation.
that could be true.
Cut those out,
Right.
and get a big boost.
That's a good suggestion. Thank you. Anything else or?
Anyone else? I will quickly check again if anything's in the chat. I don't think so though. Okay, one last question from me.
Oh, yeah.
What is your future work for this? Are you thinking
As
about-
far as future work, one thing that would be obviously nice would be to sort of go through the different PGO passes and see and try and isolate them, see which ones might be slowing them down, which ones might be speeding them up. So to just systematically go through them to see which ones work and which ones don't. This is more of a blanket approach where we just analyzed the existing PGO passes as a whole, but more work would be nice. It would be nice to have more work done on analyzing the individual passes. And again, there are also some ideas for different things we can do with this PGO data, like selecting the optimal number of teams and the optimal number of threads for a particular loop, things like that, as using the trip count to estimate these things and specify them beforehand, things of that nature. I think this is pretty recent work, and I think there's a lot more that could be done with it. So thank you for that question. Anything else or anyone else? Or
Let's thank our speaker again. Thank you.
all right. Well, thank you all for listening again.